Welcome students. In this class we will be learning how to integrate this using Feynman's technique. Now everybody call this as Feynman's technique, but it is imperative to understand that it was not Feynman who is the author of this technique. It is actually Leibniz who discovered this technique, who applied this technique, or you can use the word invented the technique, or the better word is, I think the better word is discovered. And Feynman was the one who popularized it. So having mentioned that, let us learn about this particular technique. Now you might be wondering, okay, let me just solve this using integration by parts, but it is not going to be working out. Using integration by parts, you will not be able to solve this. And that's why we are utilizing this technique. So foremost, what I wish to do is I would like to rewrite this as 2 times integral 0 to infinity sin x over x dx. Now you might be asking me, why am I writing it like this? Because if you were to take f of x to be equal to sin x over x, clearly f of x is even. Since f of x is even, we got a property. Suppose you got a to a f of x dx. If the function is even, then you can write it as 2 times integral 0 to a f of x dx. So all because of the property of integrals. So I have got this. Now what I wish to do is I would like to define a new function of this form. I of u is equal to integral 0 to infinity sin x over x times, you can add another function. You can add either a logarithmic function or a trigonometric function or an exponential function. Now it is imperative to understand, if you were to add a trigonometric function or a logarithmic function, it would not be possible for you to solve it. So the most appropriate function is to add e raised to the power of ux times dx. Right? This is the most appropriate function. Exponential function is the most appropriate function. Now even in exponential function, you cannot just leave the exponent over here to be empty. In other words, it should be converted into a negative exponent. Why? Because we got a limit as infinity. And we all know e raised to the power of negative infinity will lead us to 0. So that is our objective. We want the function to terminate. And the best way to let the function terminate or to gravitate the function towards termination is to place a negative sign. So this is a function of u. Now having defined this function, now clearly you can see we got 2 variables. We got x and u, and this is the function on the left hand side defined as I of u. Now what I wish to do is I would like to operate on both the sides by d over du. So d over du of I u is equal to d over du of integral 0 to infinity sin x over x e raised to the power of negative ux times dx. Now differentiating this function would give me I dash of u. Now what I wish to do is I would like to move this total derivative inside the integral. Now since I've got 2 variables, I cannot place a total derivative there. I need to place a partial derivative. So the partial differentiation is dou over dou u of sin x over x e raised to the power of negative u times x, right, times dx. Now since x is not connected to the functional variable u, what I wish to do is I would like to move this x component out. So if I were to move this x component out, I would have this to be equal to integral 0 to infinity sin x over x. So the differential is going to be dou over dou u of e raised to the power of negative ux, right? So this is blocked times dx. Now if I were to differentiate this, differential of e raised to the power of ux. So u is the variable, x is the constant. So I will have an x and a negative sign. So I place that. And differentiation of e raised to the power of negative ux is going to be e raised to the power of negative ux. So this is going to be sin x over x times e raised to the power of negative ux times dx. The limits are 0 to infinity. On the left I got I dash of u. Now x and x gets cancelled, giving me negative of integral 0 to infinity sin x e raised to the power of negative ux times dx, because this is the term that we ended up with. Now you can either do by integration by parts, or you can replace sin x with the equivalent of exponential formulae, which we already know, and then subsequently you can integrate that. Now what I used to do is I would like to use integration by parts. Now in this case it doesn't matter which term you take it as u. You can take either u to be as sin x or u to be as e raised to the power of negative ux. So what I wish to do, I would like to take the differential and the integration term in this fashion. Now since it involves trigonometric function, it be successive differentiation and integration. So we need to be prepared for that. So this entire term is equal to, I'm going to place the terms here. So I'm going to start off with e raised to the power of negative ux as the differential first term and sin x to be the integrating term. Now if you were to differentiate e raised to the power of negative ux, you get e raised to the power of negative ux. Since the variable is x, the constant is negative u, so you place the negative u there. Now you were to integrate sin x, you get negative cos x. Now you differentiate e raised to the power of negative ux, there is a negative sign, so that would mean we'll have a positive sign, and constant is u is multiplied here, so that would give us u squared, followed by the differential of e raised to the power of negative ux, that's going to be e raised to the power of negative ux. And integrating negative cos x would give us negative sin x, so there isn't any much change with reference to the sign. So we start out with the positive, and then we have a negative, and then we have a positive. So if I were to write all of this terms in uv negative integral v du form, so I start with this and then follow it up with this, and then I place this as the integrating term. So this is going to be e raised to the power of negative ux times cos x, so there is a negative sign there, followed by negative negative positive times negative, that's going to be negative, and then u times e raised to the power of negative ux times sin x, followed by positive into negative, that's going to be negative u squared e raised to the power of negative ux times sin x times dx. The integral sign is actually stretching from 0 to infinity. Now on the left I've got this, so I need to move this to the left hand side. So if I had to move this to the left hand side, I would get integral 0 to infinity sin x e raised to the power of negative ux times dx positive u squared e raised to the power of negative ux times sin x times dx, limits are 0 to infinity, is equal to negative of, in fact I could have taken e raised to the power of negative ux, anyway it's okay, e raised to the power of negative ux times cos x. If I were to take negative out, this is going to be positive of e raised to the power of negative ux, there is a u there, so place the u, times sin x. Now u squared is actually a constant, so it can come out. If it comes out, this is going to be rewritten as, because if I were to take 0 to infinity, e raised to the power of negative ux sin x times dx, I would have 1 positive u squared over here as a scalar quantity. This is equal to negative e raised to the power of negative ux, right? So probably in the next step I will take that down. So times cos x positive u times e raised to the power of negative ux times sin x. So what I wish to do is I would like to take this quantity out, e raised to the power of negative ux out, right, and then write this as cos x positive u times sin x. I can move this down, so this is going to be 1 positive u squared, and on the left I got 0 to infinity e raised to the power of negative ux times sin x times dx. So this is what I have got. If you were to substitute the limits, say 0 to infinity, I can just show that to you. So when x is tending towards infinity, e raised to the power of negative infinity times x, this entire quantity is going to be 0, right? As I mentioned to you, e raised to the power of negative infinity will tend to 0. As x tends to infinity, this quantity will be tending towards 0. So the upper limit is producing 0 followed by negative of negative. So if I were to have a negative of negative, this is going to be a positive quantity, right? Upper limit minus the lower limit. So my lower limit is this. Now if I were to set x to be tending towards 0, what happens when x tending to 0? So this is going to be 1, this is going to be 1, this one is going to give me 0, right, because x is tending to 0, this is off, and this is divided by 1 positive u squared. So what would this happen? I mean, what would this lead us to? This negative of negative is going to be positive, so you would have 1 over 1 positive u squared. So this is the solution that we would get. Now actually we ended up with this, right? I dash of u is equal to negative integral 0 to infinity sin x times e raised to the power of negative x times dx, and that integration is obtained over here. Now take this value and then substitute here. So this is equal to negative sign stays here. Just place this 1 over 1 positive u squared. Now this is I dash, but you need to obtain I of u. So we need to integrate both sides. That's exactly what I'm going to do. Integrating both sides, we get, so what do we get? When you integrate this I dash of u, you will get I of u. This is going to be negative integral du over 1 positive u squared, and this is nothing but tan inverse of u. Since it's indefinite, it's going to be having arbitrary constant, and you got a negative sign, so just place that. But what did we define I of u? But we know that, what do we know? We know that I of u is equal to integral 0 to infinity sin x over x e raised to the power of negative u times x times dx. This is what we got. So equate both these. So equate this, if I were to take this as sum 2 and sum 3, equating 2 and 3 we get. So what do we get when we equate 2 and 3? So this is going to be negative tan inverse of u positive c is equal to integral 0 to infinity sin x over x e raised to the power of negative ux dx. So clearly we can see that the limits are stretching from 0 to infinity. Now I need to get the value of c. So let me allow u to tend to infinity. So setting u tending to infinity, what happens? This is going to be negative tan inverse of infinity positive c. Now when u tends to infinity, e raised to the power of negative u times x will become equal to 0. So this is going to be equal to 0. But tan inverse of infinity is going to be pi over 2. You got a negative sign, positive c is equal to 0. This implies c is equal to pi over 2. Now you got c is equal to pi over 2. Take this pi over 2 and substitute it in the initial definition. So we have an initial definition, right? So we defined I of u to be this, right? So therefore you write that. Therefore 3 will imply integral 0 to infinity sin x over x e raised to the power of negative ux times dx is equal to I of u to be equal to tan inverse of u plus c, right? So you can write that down, tan inverse of u plus c. So with a negative sign, negative, because that's exactly what we got. Yeah, see that? This is what we've got. So tan inverse of u plus c. What is my c? C is going to be equal to pi over 2. Now I need integral 0 to infinity sin x over x times dx. I don't need this e raised to the power of negative ux. So what I'm going to do, I'm going to set u to be equal to 0. If I were to set u to be equal to 0, I would get integral 0 to infinity sin x over x times dx is equal to, this is 0, so this vanishes when u is equal to 0, and what it remains is pi over 2. So integral 0 to infinity sin x over x times dx is equal to pi over 2. But this is not required. What is required? We need this. If you were to see the original problem, we have to find 2 times integral 0 to infinity sin x over x times dx. So that is equal to 2 times of integral 0 to infinity sin x over x times dx is pi over 2. So substitute that. So 2 gets cancelled, giving me pi units. So that is the final solution. Thank you students, enjoy your day.